Let's start with the notion of tree width and tree decompositions, first of all. What's a tree decomposition? A tree decomposition is a way of decomposing a given graph in a tree-like way. Tree-like way so that from afar, if it looks like a tree, then this decomposition brings out this property that it does look like that. Right? So I've drawn the graph in the background. I won't normally do that. I usually just draw these circles. And now, if you stand right back, you will see a big tree with 1, 2, 3, 4, 5, 6 nodes, perhaps. If you like, you can make those visible. No, can't. This Korean chalk is very carefully coated so that you can't draw wrongly. It's perfect chalk, except for this one property. So there's the tree that you can see from afar. Right now, the question now is, okay, if that's the intuition, how do we make it precise? So given a graph, how do we define these subsets of vertices or subgraphs or something precisely? And how do we encode the fact that they do in fact look like a tree as they're arranged together? And that brings us to this definition. Tree decomposition is a family of a family V of vertex sets indexed by the nodes. I say nodes rather than vertices to distinguish them from the vertices of the graph, by the nodes of a tree T. So a tree decomposition of a graph G is a pair tree family. The family has as elements vertex sets, subsets of the vertices of our graph, and they're indexed with the nodes of that tree. Okay, but that's not all, because, I mean, anyone can use the nodes of a tree as an index set for anything at all. It doesn't mean that the graph represents anything or has anything like the tree structure which this tree is meant to represent. So we need a little more than saying that we index these sets by the nodes of a tree. We have to write down how the graph actually resembles that tree in some way. And there are the three axioms that are intended to ensure that. The first axiom just says that the bags, these VT, are called bags. These sets of vertices are bags, but they cover all the vertices of G. Okay? Fair enough. We want to decompose the entire graph G, so we'd better cover all the vertices with the bags into which we're decomposing the graph. The subgraphs that these bags induce I call parts. So parts as in parts of a decomposition. You decompose the graph into parts, right? And the second axiom says something about the edges of G, and it says that every edge has to lie in a part. Okay? So this prevents edges from connecting vertices, which we already know lie in some parts, because that's axiom 1. But we're not allowed to join up vertices by edges unless the two vertices are together in some common part. So this is not allowed. And you can see why it's not allowed. Right? Because if it were allowed, then the graph wouldn't really resemble the tree structure of the tree that it's meant to be represented by, right? So those edges are disallowed by axiom 2, and then there's axiom 3, which is a little technical. The idea of 3 is to prevent. So this is all still perfectly allowed. I'm just extending the tree a little bit. So but we're not allowed to have bags like this one here that, if they were allowed, would form something like a cycle in the tree structure. Right? So if, say, the tree structure extends as far as this, then axiom 3 forbids that there is a non-empty intersection there. It forbids a vertex from lying in the intersection of two parts unless this vertex lies in every part on the way from the one part in which it is contained to the other part it is contained in, where on the way is in the tree. So once more, the axiom says that if we look at a vertex of the graph and it lies in two different bags, indexed by little t and little t prime. So this is t, and this is t prime. It lies in these two bags. Then axiom 3 says that for every t double prime on the way, in t, in big T, from t to t prime, the vertex has to lie also in the bag indexed by t double prime. Okay? Now, there's a common phenomenon here which is, I think, interesting beyond our immediate topic, and that is we have some idea of what we want to forbid. We want the tree to reflect the structure of the graph, and if we allowed such an intersection here, we would think, oh, well, it doesn't really reflect the structure of the graph, because in the graph you can somehow get round here, and in the tree you can't, so it isn't quite right, so we forbid something. Now, does that actually achieve our aim? Is it true that for every graph and every decomposition that satisfies axioms 1 to 3, the tree really does reflect the structure of the graph? Well, the answer is, what can you say? That's not a well-posed question. That's not a well-defined question. It is a very relevant question, though. And only time can tell whether someday somebody comes up with a graph decomposition and says, well, I would like that to call that a tree decomposition as well, because it's really nice, and the decomposition is such that it does look like a tree, and so on, but it doesn't somehow satisfy these axioms. Then what? Then we have two ways to deal with it. One would be to say, oh yes, that's right, we forgot an axiom, and let's have axiom 4 as well. Or let's modify axiom 2.5 a little bit or something. So we can change our rules, or we can just leave them in peace and say, right, here's another notion. And let's study those other tree decompositions as well. And then everybody is free to decide which tree decomposition they work with. So that's how science and mathematics progresses. We don't have fights over what are the right notions. We sometimes do frown a little bit about, on the notions that somebody else comes up with, but frowning is all that's allowed. We don't sort of go to war as some people in other subjects do. In mathematics, we're peaceful. So that entails keeping our minds open about the question of whether a definition is right or not. Yet at the same time, it's very much our quest to get the definitions right. There's lots and lots and lots of senseless effort invested in silly definitions. So it's a wholly sacred process here that we have to treat with respect, but also be responsible about ourselves. Okay, end of philosophy. Back to maths. There are some more definitions I want to give you. And here they are. So we have bags, we have parts, then these subsets here are adhesion sets. Of the decomposition, and the adhesion of a given decomposition is the maximum size of such a set. So sometimes we want to impose the property on the decomposition that these overlaps should be small, and then we say we consider it a tree decomposition of adhesion less than 17. Okay? So the adhesion is the largest size of an adhesion set, and the adhesion sets are these sets here. Okay, and then there's one more definition. If we look at a part and we add some edges between all vertices in a common adhesion set, so, for example, we would add this edge here. These two vertices are not adjacent in the graph, but we would add them, add the edge between them, because they lie in a common adhesion set of this part. If we do that, then this thing is called a torso. It's a torso of the decomposition, or in particular, a torso of this particular part, V G, induced by V T double prime. So why is that called a torso? Anybody see a torso? No? Okay. Can anybody see a torso? Thank you. So with all these made complete, That's it also. So by the way, it's not forbidden that parts contain each other. So that would also be a tree decomposition, or that, right? So all these are allowed. Good. Questions about the definitions? Yeah? No? Okay, then let's have our first lemma. It says that when we consider adjacent parts in a tree decomposition, these two, then their intersection, so they're called T1, this is VT1, the bag, and this is VT2, then the intersection here of VT1 and VT2 separates the graph. And how does it separate the graph? Well, these two parts are adjacent, I said. I just used that word. What I meant was that T1 and T2 are adjacent nodes in that tree. So when you delete an edge in a tree between two adjacent nodes, then you get two components of that tree. And you can now form the union of all the components, of all the bags that are indexed by a node in one component. So for the part V, or the bag VT1, call that U1. And you can take the union of all the other parts, call that U2. And then the assertion now is that this little separator here between just these two bags, separates the graph. Let's skip a little to a lemma that comes a little later in the book. And that's a nice lemma that tells us it's a very simple case of a much more general phenomenon. And the assertion is that if we take a complete subgraph of G, then that will lie in some part. It's sort of plausible, right? You can't have edges like this. And so how do you prove that properly? Have a complete subgraph, call it K, of G. Find a part in which it lies. Yeah, I mean, you could start with one edge of K and say, well, that must lie in a part. So do all the other edges lie in that part too? No, not really. So my edge could lie in this part because it's here. And then the other edges might lie here rather than there. And then I could say, okay, I'll change my mind, but maybe there's a third part here. So let's do it formally. And there's a very, very sort of simple and nice formal proof. And that goes as follows. Notice that if you have a separation in a graph, it's just one separation, like U1 and U2. Any complete graph will lie on one side or the other. Right? It can't have a vertex here and a vertex there, because if it's complete, it would have to contain that edge, but that's not allowed in a separation. So either it lies in the intersection, that's fine, or as soon as it has a vertex in one of the sides minus the other, then all the other vertices are forbidden from lying in the other side minus the one, so they have to lie somewhere in that side. So every complete graph, unless it lies in the intersection, puts an arrow on that separation. So let's do that for the tree. So we have our tree decomposition, and we have those nodes of the tree that index these parts and bags. And now we have our complete graph. And for every attachment set, for every adhesion set, either the complete graph lies in that adhesion set, in which case we've already found 2 parts even that contain it. That's overkill, that's fine. But if not, if it doesn't lie in that particular adhesion set, then it lies on one of the 2 sides. So we get an arrow on this edge of the tree, right? Pointing towards the node that is the index of the nearest bag on that side. So it would be T1 or T2 in our earlier lemma. So in this way, every edge gets an arrow imposed by our complete graph. And if you follow the arrows on a tree, on the edges of a tree, you can't go around in circles because a tree doesn't contain cycles, so you'll get stuck somewhere. You might get stuck in a leaf, you might get stuck in a non-leaf, but wherever you get stuck, you will see that any arrows of outgoing edges from that node will be pointing towards you. That's why you're stuck. Okay, consider such a sink. Maybe there's more than one sink. There isn't, but never mind. So let's look at such a node, T, and I claim that the part that belongs to it, G of Vt, contains our complete graph K, that it lies somewhere in there. Right, and why does it? Well, because of how these arrows are defined. So this arrow here, what does it tell us? It tells us that K lies in the UI, earlier in the lemma, that is the union of all the parts or indexed by nodes in the subtree of T minus this edge that marks this, that has the arrow there that we're considering, where little t is the first node. Similarly, this arrow tells us that K lies in the union of the parts indexed by the nodes in this subtree here, the whole tree minus this edge, that contains T. So and similarly for this as well. So by definition of these arrows, K lies in the intersection of the U's, the big sets UI, that correspond to these components of tree minus that one edge that contain T. since we are taking the intersection over all the edges at T, there's only one node in that intersection. There's only one node that lies to the left of this edge, to the right of that edge, and below this edge. There's only one node, and that's T. So since K lies in every UI corresponding to these subtrees, it must lie in the intersection of all these UIs, and the intersection of all these UIs is precisely this bag. Okay, we'll have other applications of the same idea later, so it would be good if you understood that proof. It's much simpler than I made it look. So do you have any questions right away? No. Okay. So properties of tree decompositions. One property is that when you have a tree decomposition of G and you take a subgraph, then it inherits that tree decomposition if you wanted to. Right, so once more, you have a tree decomposition, you have all these bags, V little t. The little t's are nodes of a big tree. You can copy that decomposition to the subgraph H of G. And what are your new bags? Well, they're whatever of H lies in a given VT. So the bags are VT intersection vertices of H. Why is that a tree decomposition of H? Well, because the three axioms continue to apply. Right? The first axiom says every vertex has to be covered. Yes, every vertex of G was covered, and now we just cut them down to the vertex sets of H. So every vertex of H is covered. Every edge is covered. Well, it used to be, so it still is, because it has both its ends in H, if it is an edge of H. And the property, the third axiom, where any vertex lying in two bags has to lie in every bag on the way, that's just true because it used to be true. Okay, so that's easy. And more interestingly, tree decompositions are also passed on to minors. Nice. So take a minor. So what's a minor of G? Well, we have all these connected sets that we contract, right? They don't have to cover all the vertices. They're just connected sets, and we have edges between these connected sets. Whenever one of them had an element, a vertex of G, adjacent to an element of the other. All right, so those are the branch sets of R minor, what should we call them? XH. H a vertex of the minor H of G. Right. So now our aim is the same as before. We have this decomposition of G. Here are the white bags. And we would like to get from it a decomposition of H. So that's not so clear. If our plan works, then we have to say, then we want a decomposition, white is better, a composition Vt, T of t, indexed by the same nodes that used to index our decomposition of G. But how should we define these WTs? How should we define the bags for H? So given our little index T, which vertices of H do we put in WT? Not so clear. Here's our node Vt. This is Vt. That defines our little t, or the other way around. And now, do we put this branch set here, this, do we put the vertex of little h, whose xh is this branch set, do we put that in WT or not? Do we put this in WT or not? The new decomposition here has to cover all the vertices, that's the first axiom, and also has to cover all the edges. Now, what are the edges between h's? These edges here, right? So this is h prime. And these edges between different nodes or vertices of big H come from edges of G between elements of their branch sets of which they're indices. So these two blue vertices here are adjacent only because these white vertices are adjacent in G. Now, the white vertex we knew has to lie in a bag. So if we want the blue vertex to lie in a bag here, we'd better include in that bag both these vertices, H and H prime. Right? So that leads to the definition of W as the set of all those little h's of big H that meet the corresponding bag of the decomposition of T. So WT is the set of all little h's whose branch set XH meets VT. Right, now we've defined our family of WTs, indexed again by the nodes little t of our big tree. And now we need to show still that it's a tree decomposition of H. So why is that? Okay, so that's the definition. Is that a tree decomposition of H? Well, first axiom, it has to, the WTs have to cover all the vertices of H. Do they? Yes. Because take a vertex of H, that comes from a branch set XH. The branch set XH has vertices of G in it. Those lie in certain VTs. And for all these T's, H will lie in WT. So that's clearly true. Same for edges, exactly the same argument, right? Every edge of H comes from an edge of G that lies in some VT, and the edge of H lies in the corresponding WT. But how about axiom 3? So now we have a, does that fit in there? Yeah, perhaps. So now we have a vertex of H that lies in different WTs. And we want to show that it lies in every WT on the way. So this is my best candidate for a big vertex. So this little h here, that lies in this little h lies in this WT here. That corresponds to this T. And it lies in this WT prime. So since it's white, I write V's there, right? But I mean this H here lies in WT and WT prime. That's what I'm assuming. What does it mean? It means that the branch set meets VT and VT prime. That's just the definition. Okay, now we want to show that this little h lies in every WT something else on the way in the tree between T and T prime. Why does it? Well, because XH branch sets are connected. So that's a connected set in G that meets VT. That's because little h lies in WT. And it also meets VT prime. That's because h lies in WT prime. And in this connected set, I can find a path between those two vertices. But now we have the separation lemma for G. And the separation lemma for G tells us that this path here meets, in other words, has a vertex in, sorry, that's a white path. That's a white path, a path in G, between these two vertices in the branch set of XH, and the path lies in XH. So this path goes from VT to VT prime. So it lies in every VT double prime on the way between T and T prime. And if this vertex here lies in some VT double prime, then that puts H in WT double prime, because this vertex lies in the branch set of H. Okay, so we do need a little bit. We need that branch sets are connected, otherwise it's not true. I could have convinced you, perhaps, of all this half path without mentioning that branch sets are connected, because it's so easy to get confused. But one does need that, otherwise it's not true. Yeah, okay, so we have shown that tree decompositions are passed on to subgraphs in the obvious way, but by just intersecting the bags with the vertex head of the subgraph. And they're also passed on to minors in this way. Okay, so here at this point I want to inject a little theorem, actually not a little theorem, but a theorem about k-blocks, because it plays to the same tune as the complete subgraph big K sitting in some suitable bag or part that we had a moment ago. So let me tell you what a k-block is. A k-block in G is a maximal set of at least k vertices, no two of which are separated in G by fewer than k vertices. Okay, so for example, a complete KK subgraph is clearly a k-block. You can't separate any two of its edges, its vertices by anything, and it also has at least k vertices. A k-connected subgraph is a k-block. It has at least k vertices, and you can't separate any two by fewer than k other vertices. But there are rather different examples as well. So for example, if we take not just a complete graph, but subdivide every edge maybe 1,000,000 times, maybe not, then the branch vertices of this TKK, those form a k-block. Right, this whole graph is not even 3-connected, right? Because there are all these little inserted vertices, subdividing vertices here, so you can separate this vertex by deleting those two from everything else. Right, so this graph is not even 3-connected, but it has a k-block, namely the branch vertices of that TKK, because there's k of them at least, and no two of them can be separated by fewer than k vertices in the graph. And another good example is a large grid. This grid just provides connectivity, and the k-block is going to be something else. The k-block will consist of vertices placed around the perimeter of that grid and made adjacent to at least k vertices on that perimeter. All right, and now if you take at least k orange vertices, then again, you cannot separate any two of them by fewer than k other vertices, because you can reach this grid and you can reach this grid here. Well, let's make this, put all these neighbors on the same side, and then you cannot separate these from those by fewer than k vertices. That needs a little bit of puzzling over that problem. All right, so you can sort of find your way here. Okay. So that's another example of a k-block that is very unlike a complete subgraph or even unlike this, because this whole graph can be planar. Right? So a planar graph can have k-blocks for arbitrarily large k. They're highly connected sets, vertex sets, where the connectivity is not between these vertices themselves, but somehow in the rest of the graph, highly connected in some different sense from k-connectivity. And the theorem says, I'm not going to write it down, but I'm going to tell you, the theorem says that every graph has a tree decomposition with the property that these blocks are subsets of different parts. Right? They're nicely separated by this tree decomposition. Like the K that we had that was a complete graph lies in a bag so does every k-block. Why is that? If a separation has order less than k, only then will a k-block lie entirely to the right or entirely to the left, because if it had a vertex on the left and on the right, then those fewer than k vertices would separate them, so they couldn't be in the same k-block. Okay, so we have a tree decomposition. So for k fixed, it has a tree decomposition of adhesion less than k. So these separators all have size less than k, such that every k block lies in some part. Even more is true if two k-blocks, which we know lie in different parts, are separated in G by I vertices, where I is the smallest size of a separator, so that one lies entirely to the left and the other lies entirely to the right, then one of these adhesion sets on the way from this part to that part also has size only I. That's what we call that the tree decomposition separates these blocks efficiently. So you get as small a separator from these adhesion sets as you get in the real world in G. Different k-blocks cannot contain each other. So there is a separator of order less than k that distinguishes them, that separates the two. Why is that? Here's a k-block. There's another k-block. They don't contain each other because they're both maximal. So pick one vertex that is not in the other, and this has a vertex that is not in that. And then those two are separated by a separator in G of size less than k. If not, if every such pair of vertices was not separated by such a separator, then they would all be part of the same k-block. Okay, so every two k-blocks are separated by fewer than k vertices in the entire graph, and the tree decomposition has this property that such as small, for every two distinct k-blocks, they live in different parts, and some such smallest separator can be found among the adhesion sets on the way from this part to that part. Okay, next topic is tree width. So, given a tree decomposition here, the width of that tree decomposition, morally, is the largest size of a bag. Why am I saying morally? Because it's not true. It's the largest size of a bag minus 1. So, for example, if the graph itself is a tree, then a tree decomposition that minimizes the largest size of a bag consists of all k2s. So if the graph is, if this is our entire graph, then what's the tree decomposition? Which tree decomposition has the smallest maximum size? It's this tree decomposition here. Right? And now, when Robertson and Seymour invented tree decompositions, well, they didn't actually invent tree decompositions, but they invented the notion of tree width. They wanted trees to have tree width 1 because they look so nice and slim. So they said, okay, it's the maximum bag size minus 1, because here it's 2. Okay, so unfortunately, to this day, the width of a tree decomposition is the size of the largest bag minus 1. And the tree width of G is the smallest width of any tree decomposition. So if we fix a tree decomposition, its width, so the size of the largest bag minus 1, can be quite large, because we might have chosen a stupid tree decomposition, for example, just one bag, right? But if we want to decompose G in a tree-like way, then we would like to pick a tree decomposition that is not stupid. So we're looking for a tree decomposition whose bags are as small as possible, and our first version of smallest possible is that the largest size is minimum. And the width of that decomposition, i.e. the order of the largest size of that decomposition, minus 1, is the tree width of the graph. So a graph has a tree width, a decomposition has a width. So here's a corollary. Since minors inherit tree decomposition, the tree width cannot go up when you take a minor. So the WTs, can they be bigger than the VTs? My claim is that they can't, because branch sets are disjoint, right? If you have your VT, so this branch set here eats away some vertices, that eats away some vertices, that contains some vertices, but branch sets are disjoint. So you can't have more branch sets intersecting a given VT than VT has vertices, so you can't have more H's in WT than VT has vertices, because every such H needs a branch set to intersect VT in order to qualify for being in WT. Okay, so the tree width of a minor is no bigger than the tree width of a graph, and the consequence of that is that the class of graphs of tree width less than k, for any given k, is closed under minors, right? Then the minors also have tree width less than k. So come up with a small set. In practice, it will be the set of all minor minimal graphs not of tree width less than k. Right, and then the graphs of tree width less than k will be precisely those graphs that don't contain one of those as a minor. Okay, what if k is 2? Which are the smallest graphs that don't have tree width less than 2? Yeah, k3. Right? Forests are acyclic graphs. Every graph that is not a forest contains a cycle. And there's a unique minor minimal graph that has a cycle, and that's a K3, or C3 if you like. Okay, so this class of graphs, those of tree width less than K, for K equals 2, is defined by excluding K3. What about K equals 3? Well, that's not quite obvious, but the same trick works. So the minor minimal graphs of tree width not less than 3 are the K4s. So the proof of that is in the book. It's a little pedestrian, and so I'm not showing you how it works here, but it's easy. All right? So a graph has tree width less than 3 if and only if it doesn't contain K4 as a minor. Right, and how about bigger K? Well, for arbitrary K, nobody knows. But it's really important on our way to the graph minor theorem, the theorem that all the graphs are well quasi-ordered by the minor relation, that the graphs of bounded tree width are well quasi-ordered by the minor relation, which means that the minimal forbidden set that characterizes that graph is finite. So indeed, one of the first steps in the proof of the graph minor theorem was to prove that the graphs of tree width less than k for any fixed k is indeed well quasi-ordered. So that's a very small subgraphs of the class of all finite graphs, but that was the first step. So now is a fun question. Can you do that for k equals 2? Right? So the graphs of tree width less than 2, we know what they are. Are they well quasi-ordered? The incorrect answer is yes, of course they are. That's Kruskal's theorem. What is the correct answer? Kruskal's theorem says that the trees are well quasi-ordered, right? But the graphs of tree width less than 2 are not just the trees, they're the forests. So are the forests well quasi-ordered? Yes, by Hickman's lemma. Right? Forests have components that are trees. And a forest is a minor of another forest if we can embed its components in those components by the embedding relation that governs trees. So that's Hickman's lemma applied to the components of forests. Right. Okay. Next topic is some particularly good tree decompositions. Take a big KR and let a long path emanate from it. And now take the following tree decomposition. Take, obviously, this as a bag. That's R vertices. We need that inside one bag, as we know. Right? Any complete graph has to sit inside a bag. So the smallest size of a bag is going to be R. Right, now, even if we want a tree decomposition of minimum width, we can afford to make the other bags, give the other bags size R as well. And that's really wasteful. It's still an optimal tree decomposition because these poor fellows here simply don't matter. This one is getting all the attention. But it would be nice if here we chose just those bags that are morally the right ones, namely those. Right? And here's another wasteful tree decomposition. We have our KR again. Now let's take two such bags, two such paths, and let's be wasteful in a different way. For example, this is a bag, need that bag, and now just take those bags of size 4. 4 is, as everybody knows, less than R, so that won't matter. They're not getting any attention. This captures all the attention. And yet it's wasteful. Right? We would like as parts just those K2s and those K2s. That would be a much better tree decomposition that shows the tree shape that this graph has in a better way. This doesn't really show the tree shape as well, because this has 2 branches. The graph has 2 branches, but the tree decomposition only has 1 branch, the tree. Okay, so here's the definition. For every 2 vertex sets, Z1 and Z2, you can find, say, both of size, at least give it a name. No, let's say they have the same size. Let's call that size k. K has nothing to do with the tree width. Okay, so take any such vertex sets, each sitting in some part. Either you can find k disjoint paths from one to the other, or you can find an adhesion set of size less than k that separates them. So here we could have this as Z1 and this as Z2, right? And k is 3, say. Then we certainly don't have 3 paths from one to the other. We have only at most 1 path from one to the other. But all the adhesion sets on the way have size at least 3. Right? So this example would be nicely killed by that definition, which is our aim. So with this example, so if we took this as Z1 and this as Z2, okay. So here we have only at most 1 path from Z1 to Z2, but there is no adhesion set between the node, the part that contains Z1 and the part that contains Z2. Why isn't there one? Because it's the same part. So that's a property of this definition, which I glossed over by drawing Z1 and Z2 so spaced out as here. It's quite okay to consider Z1 and Z2 in the same part. And then the same assertion has to hold, so there must be k paths. But the linking doesn't have to happen inside that path here. So, for example, if these are Z1 and Z2, then these two vertices here could be linked in that way. Right? Okay, so the definition of a lean tree decomposition is that whenever we pick 2 bags and sets of vertices of the same size in these 2 bags, 1 in each, then there are that many disjoint paths from one of the 2 vertex sets to the other, unless there's an adhesion set of smaller size between them, between these 2 bags. Okay? Cool. Right, and now comes something unexpected. You can get such a wonderful lean tree decomposition for free. For free meaning that you can have one of minimum width that in addition is lean. So these decompositions, these bad ones here, have minimum width, but they're anything but lean. So you can optimize a tree decomposition locally, as the definition of leanness implies. I haven't shown you that. I haven't even defined what it means, but that's what it's meant to do. You can optimize this locally without any jeopardy to the global optimum that tree decomposition has by minimizing just the size of the largest bag. Okay. And then there's one more notion that I want to show you. Strengthening of tree decomposition. And that is, you might require that the bags should be connected in G. Right, after all, if the tree decomposition resembles something like the real structure of G, then what are these bags? They're the knobbly bits in that tree, right? And the knobbly bits shouldn't be knobbly bits if they weren't connected, right? So it's a reasonable requirement. So a connected tree decomposition is a tree decomposition whose parts are connected, and the connected tree width of a graph is the smallest width of a connected tree decomposition. And now the question is, can that be achieved like leanness for free? And the answer is no. And the simple reason for this is long cycles. So if we take a CK, can you see its tree width? That requires a certain degree of perversion, so you may be finding it hard to see it, yes? Yeah, that's right. So the tree width is 2, and the decomposition is, well, I won't do that to this cycle, it's horrible, but you just redraw the cycle like this. So if the tree width is 2, we're allowed bags of size up to 3. These are the first 3, then I add one at the top, now I add one at the bottom, now I add one at the top, now I add one at the bottom, and so on. So I can cover that whole thing by bags of size 3, but these bags are not connected. They always contain a vertex, an upper vertex and a lower vertex. And it's damn hard to find an optimum or optimal connected tree decomposition of a long cycle. I hope that's going to be an exercise on the next sheet. It's not on this sheet. So I can tell you the answer. Yeah, okay. So the connected tree width of CK is, I think, half K. Yeah. Half K rounded up. Okay. That's a very beautiful exercise. You need Friday's lecture to tackle it. Don't try it yet. And there's a nice theorem that goes with it. First, a lemma. Oh, no lemma. Yes, there's a lemma. That says that if such a long cycle is contained in a graph, then the connected tree width of that graph will inherit the lower bound that comes from that long cycle, as long as that cycle is, well, here's a long cycle. No, I can use this. If I add all these missing edges, right, then suddenly we would have a connected tree decomposition with only 2. So long cycles as such don't force the connected tree width up if they're contained just as subgraphs. But if they don't have chords like this, more generally, if they don't have shortcuts like this, then they do force it up. So cycles are called geodesic in G if there are no shortcuts. If the distance between any two vertices on the cycle in G, taken in G, is no smaller than the distance on the cycle. So it's locally shortest everywhere. And if CK is contained in the graph as a geodesic cycle, then the connected tree width of that graph will indeed be at least this, half k. And the theorem is that this, together with obviously large tree width as such, are the only two obstructions to large connected tree width. So that's a beautiful theorem. It's best possible in this very, very nice qualitative way, proved by Malte Müller. Malte Müller was a PhD student here a few years ago, and that was in his thesis. So the connected tree width of a graph is bounded above by a function of two parameters that can obviously drive it up. And the one is the natural tree width. So if a graph has big tree width already, it can't have smaller connected tree width, obviously. And if it has long geodesic cycles, CK for a big K, then it also has large connected tree width. And so the converse of that is the assertion of the theorem that the connected tree width is bounded as a function of the real tree width and the longest length of a geodesic cycle, f of wk. So, yeah, and that is it for today. I'll show you some certificates for large tree width in the next lecture and prove a biggish theorem about that. And that will be tree width then, I think, for good. So I look forward to Friday.